Swayam Prabha. Digital India. Educated India.
So, we familiarized ourselves of how to classify molecules according to symmetry. We learnt all about symmetry operations, symmetry elements and so on and so forth. And then we went on to talk about symmetry operations in the language of matrices, and we wrote something called matrix representation. I think lecture 3 title was matrix representation. And after that we talked a lot about matrices. Basically, because if you want to write a matrix representation, then you better know what matrices are all about. So, today we come back to matrix representation once again. So, we revisit the same issue, but with a little more background of matrices. But before we do that, it is always better to behave like a bowler, go back a few steps and then come in to deliver. So, let us go back a few steps and make sure that we have not forgotten the ABCs that we require here, right. So, this is what we have been doing over the last few days. We have talked about transpose, we have talked about adjoint, or what is sometimes called a Hermitian conjugate. We have talked about Hermitian matrices and unitary matrices, and since we all know this, in fact we tested this in the last class also. Tell me what is a Hermitian matrix? Yeah, red, black, white t-shirt. What is your name? First tell me your name. Sumit. Oh, there are 2 Sumits in class. So, Sumit, tell me, what is a Hermitian matrix? A equal to A transpose. Somebody want to say something about that? Hermitian matrix? A dagger, A adjoint, not transpose, right. A transpose would be a special case if it is a real matrix, right. Hermitian matrix is A equal to A dagger. A transpose would be correct provided all the elements are real, there is no imaginary element. And what is a unitary matrix, the other Sumit? So, Hermitian is A equal to A dagger. What did you say? A into okay, right. A equal to A dagger is Hermitian and A inverse equal to A dagger is unitary. Very easy to remember. Hermitian is A equal to A dagger and unitary is A inverse equal to A dagger, or A dagger equal to E. So, Sumit, no confusion with unitary anymore, good. And what is an orthogonal matrix? An orthogonal matrix is a special case of unitary matrix where all the elements are real. When you work with a real matrix, then A transpose equal to A inverse makes it orthogonal, and today we are going to see some examples of orthogonal matrices. We have already seen some example earlier. Today we are going to see more, and today they are going to be more relevant to symmetry, right. And this is another thing that we had derived, that columns or rows of unitary matrices are related to a set of orthonormal vectors in a general vector space, right. We had demonstrated this, right. And how do you write it in summation form? Sum over k equal to 1 to n, aik ajk star equal to del ij. Achha, what is the meaning of sum over, what is the meaning of this? Let us expand. Aik, what is aik? Aik, I1, then AI1, AI2, AI3, so on and so forth. So, are we going down a column, or are we going from left to right in a row? Like this or like this? Like this, right? Because the first one, I, the first subscript denotes the row number, second subscript denotes the column number, right. So, when I1, then AI2, AI3 and so on and so forth, right. So, we are going from left to right in a row. So, the row number is constant, the column number changes. Is that all right? And then what do you have? You have AJK star, that equal to del Ij. So, when j equal to I, then it is 1, when j equal to anything other than I, then it is 0, and that is how you define orthonormal vectors, right. So, this is something that we had demonstrated, and then we had talked at length about matrix eigenvalue equation, and we said that what happens is you can have the situation where a square matrix multiplies with an eigenvector x1, x2, x3, x4, so on and so forth, xn, to give you the same column, same vector multiplied by an eigenvalue lambda. And when that happens, you write it in a matrix eigenvalue form, Ax equal to lambda x. A is the square matrix, x is the column matrix consisting of x1, x2, etc. Lambda is the eigenvalue, constant, scalar, and then again you have x. So, the small x is also a matrix, do not forget that, right, eigenvector, eigenvalue. And then we had demonstrated in the last class that you can rewrite this equation in a more convenient form, and that is A minus lambda e multiplied by x equal to 0, right. And now, if you get an equation like that, then the non-trivial solution of course will come when you have det A minus lambda e equal to 0. And you write out this determinant, this is the secular equation that you get. And as we said, the secular equation occurs in many places where you solve such a system of equations. Okay. Now, when you expand this matrix, are we all clear that we are going to get on the left hand side a polynomial in lambda of the order n, right. You know how to expand matrices, right. Now, when you equate that to 0, quadratic equation gives you how many roots? Quadratic equation gives 4 roots, just because it is quadratic. 2 roots, 2 roots. Quadratic means to the power 2. Why is it called quadratic? That's an interesting thing. Let us see how many have forgotten. So, it is to the power 2, right, x square plus bx plus c equal to 0. Why is it called quadratic then? What is a quadra? Quadra is 4. The answer is very easy, x square, bx, c, 0. There are 4 terms, that is why. So, you perhaps gave the right answer, it is just that you touched your nose like this. 4 terms, anyway. So, now these n roots that you get, they form what is called the eigenvalue spectrum, alright. So, for each of these n roots, you can write a matrix eigenvalue equation, okay. So, now it is better to add a subscript to the matrix eigenvalue equation and write it as axi equal to lambda I xi, okay. I denotes which root you are working with. And then what we said is that this xi's are all column vectors. So, instead of writing n number of equations, it is better to write one equation and combine all the column matrices into one square matrix, which is n by n. When you do that, then we write it like this, A capital X equal to capital X lambda. What is lambda? Lambda is a diagonal matrix, right, and in its diagonal it has this lambda 1, lambda 2, lambda 3, all the roots, okay. And finally, we realized that if you perform a symmetry transformation, a similarity transformation of A using X, then you get lambda. So, this is one way of diagonalizing a matrix. Perform a similarity transformation using the matrix of the eigenvectors. That should give you a diagonal matrix which will tell you all the eigenvalues. And I think last day we had worked out an example where we worked out the lambdas and then we found what is X, okay. So, you can do that for any matrix that you have. Another important point that we made was X transpose X dagger X is equal to E, or X is a unitary matrix. No surprise, because we already said that the columns or the rows of unitary matrix are associated with orthonormal vectors, and here we are working with vectors, right, the eigenvectors, fine. So, that is a unitary matrix. Now, and then we went on to prove something more. When the matrix is Hermitian, first of all we saw that the eigenvalues have to be real, which is in line with what we study in quantum chemistry. Secondly, we also understood that when the matrix is Hermitian, then the eigenvectors are mutually orthogonal. So, that is why everybody likes matrix operators and Hermitian operators and Hermitian matrices, because you get mutually orthogonal eigenvectors and you get real eigenvalues, very easy to handle, convenient system, right, and there is a lot of practical utility as well. Now, and then finally, we talked a little bit about similarity transformations. So, if A and B are conjugate to each other, then we learned that det A equal to det B. We learned that A and B have to have the same eigenvalues, they have the same traces, and lastly we said a unitary transformation leaves a unitary matrix unitary. So, some questions about the way we derived it, I suggest that you please go through Bishop, there it is worked out. So, it should not be a problem, right. Now, the question is, why are we suddenly doing all this math in a chemistry course? We are doing all this math because do not forget where we had taken off from the discussion on symmetry. That was our closing slide, right. We are talking about C2V, water, okay, very simple molecule. We keep on saying as simple as water, even though that is not chemically correct. You should not say as simple as water, at most you can say as simple as hot water. Water is an extremely complicated liquid, there are so many hydrogen bonds breaking all the time. If you heat it, then some hydrogen bonds are not there, then it becomes a little simpler liquid. Water should not have been a liquid in the first place, you know that, right? Huh? Why do I say that? Water should not have been a liquid? Yeah? So, once again, I mean, a little bit of what we learnt in our childhood, H2S is a gas, and in periodic table sulfur is below oxygen. So, if H2S is a gas, why would H2O be a liquid? It is a liquid because of hydrogen bonding, right. That is why it is a strange liquid, it is an unusual liquid, right, and that is what makes life so unusual as well, because life is all about water. So, blame it on hydrogen bonds. Anyway, so water belongs to C2V. We had worked out this representation for C2V, right, using the atoms oxygen HA and HB as the basis, okay. And then we had obtained two representations, one is a one dimensional representation which has to be irreducible, and the other is a two dimensional representation. We left this topic with the question, is this two dimensional representation reducible or irreducible? If it is reducible, how do I reduce it? How do I know whether it is reducible or irreducible? And how many irreducible representations are there? So, we had said that the answer to this will come from great orthogonality theorem, which comes from a group theoretical treatment of the problem of symmetry. And in order to be able to do this group theoretical treatment, we needed to know all that we studied about matrices, okay. So, now that we are a little more informed about matrices, now that our memories are refreshed, let us see what we can say about these matrices. 1001 is of course very boring, unit matrix, but 0110, is it a Hermitian matrix? Is it a unitary matrix? Is it an orthogonal matrix? Let us work it out. What is the transpose? Well, if it is unitary, then it will be orthogonal, of course, right, because it is a real matrix. So, first let us work out the transpose. 0110, what is the transpose? Is the same. So, A equal to A dagger or A transpose, what would you call it? Hermitian. So, yes, it is Hermitian. Is it unitary? How do you know? You have to find the inverse. What is the inverse of 0110? And since we are just asking whether it is unitary or not, we can take a shortcut and multiply 0110 by itself. See what you get. Multiply 0, 1, 1, 0 by itself, and don't be a spoil sport, let the others work out as well. Multiply 0, 1, 1, 0 by itself. Hold on with the answer. I am getting 2, minus 3, 5 and 8. 0, 1, 1, 0 multiplied by 0, 1, 1, 0. What is your name? I forgot again. Kamal, right? Kamal, what are you getting? 1001. What about you? Achal? 1001 unit matrix. So everybody has got 1001. So what do I get? A equal to A transpose, or I can also say A transpose equal to A inverse, right? A equal to A transpose and A transpose equal to A inverse. So it is unitary, and of course it is orthogonal also. It is a real matrix. It is everything, right? Everything. And of course the same holds for 1001. What is the inverse of 1001? 1001. What is the transpose of 1001? Same thing. Okay, right. Now let us turn our attention to a little more complicated matrix that we had encountered earlier. Remember these matrices? We had used the coordinates of a point x, y, z as the basis, and we had worked out these matrices for a Cn rotation. So for Cn plus, we got cos theta sin theta 0, minus sin theta cos theta 0, 0, 0, 1, and for Cn minus, we got cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1, right? Remember? You either remember or believe me, right? So these are the Cn plus and Cn minus matrices for Cn plus and Cn minus operations that we got, general representation. So these matrices also can be block factorized in this manner. What is the meaning of block factorized? You leave all the zeros outside the two lines, okay. Then you have a 2 by 2 block here, and you have a 1 by 1 block here, okay. 1 by 1 block is again 1, 1, so let us not worry about it. Let us work only with the 2 by 2 block. Now what does the 2 by 2 block deal with? Which part of the basis? What is the basis here? X, y, z, the coordinates, right? Now out of which z is unique, it forms a basis by itself, irreducible representation, it forms a representation by itself, okay. X and y are here. Why do I call it a 2-dimensional representation? Because the off diagonal elements are not 0, okay. Block diagonal elements are not 0. So I call it a 2-dimensional representation. Another way of thinking is, what is the basis here? X and y, right? How many elements are there? 2. One is x, the other is y. So the dimensionality of the basis also defines the dimensionality of the representation. So the reason why we have off diagonal element, why is it that we have off diagonal elements non-zero? What does it mean? In a transformation, what do diagonal elements stand for? What do off diagonal elements stand for? We are revising because it is very easy to have forgotten what we discussed earlier, but we do not remind ourselves of all this, then we will not understand what is going on after this. So we are basically revising. What is the meaning of diagonal elements in this transformation matrix? Which one? Diagonal or off diagonal? What are you saying? I am sorry? Diagonal elements denote the contribution of a particular vector into its own transformed form, right? And off diagonal elements, the contribution of a vector in the transformed form of another vector, right? So this sin theta, for example, there is a contribution of y in x dashed, right? X dashed y dashed is equal to cos theta sin theta minus sin theta cos theta multiplied by xy. So x dashed equal to cos theta x plus sin theta y, is that right? So the sin theta is the coefficient of y in x. Similarly, this minus sin theta is the coefficient of x in transformed y, isn't it? What is y dashed? Y dashed equal to minus sin theta x plus cos theta y, right. So, off diagonal elements are contribution of a particular element of the basis in a different transformed element, and the subscripts tell you where the contribution is coming from and where the contribution is made. Okay. So, now that we have a two dimensional representation, let us just work with that, let us forget about z and let us talk only about transformation of x and y, because x and y jointly form a basis here, so far we can see, and the whole point here is that x and y get mixed. When you turn, you cannot represent transformed x as pure x, it is a mixture of x and y, fine. So, now, so what can we now say about these matrices with the background of the last 3 or 4 classes? What is it that we say about these matrices? First point to note, are they not transpose of each other? Now, henceforth what I am going to do is I am going to call these matrices D, okay, that is the notation followed in Bishop's book. So, transformation matrices are going to be denoted as D, and when I write Dij, that means the matrix element in matrix D, okay. So, are we okay with this? DCn plus is equal to the transpose of DCn minus. Do you see this? Cos theta, if you want to transpose, take the minus sin theta here, minus sin theta, and then this sin theta should come here, sin theta, this cos theta remains where it is, okay. So, these are transpose of each other. Ziba, question, answer, okay. We will get more answers as we go along. Second point to note is this: what is the condition for a matrix to be Hermitian? We said A must be equal to A dagger, or if everything is real, A must be equal to A transpose. Are any of these matrices equal to its transpose? No, right. So, since they are not equal to the transpose, they are not Hermitian. Earlier, in the earlier example, we had encountered matrices which are Hermitian as well as unitary as well as orthogonal, right. Here this matrix, these two matrices are definitely not Hermitian, right. Next, what is DCn plus DCn minus? Multiply together and see. First row, first column, what is it? Cos theta into cos theta plus sin theta into sin theta, cos square theta plus sin square theta. What is cos square theta plus sin square theta? 1. So, first row, first column is 1. First row, second column, cos theta into minus cos theta sin theta, cos theta into minus sin theta. So, minus cos theta sin theta plus sin theta cos theta, that is 0. Second row, first column, minus sin theta cos theta plus cos theta sin theta 0, and second row, second column, minus sin square theta plus cos square theta, that is a problem. Yeah, minus plus, so not minus, no problem, right. Sin square theta plus cos square theta. I also need to see if everybody is awake. So, this is unit matrix, right. What does that mean? That means DCn plus is the inverse of DCn minus. Yeah, exactly. But even before we go there, now see, we have reached something interesting. We could have said that DCn plus is the inverse of DCn minus without doing all this, right. Think of rotation by 120 degrees. This is plus, this is minus. Are they not inverses of each other? Right? It is just that we have worked it out for a more general case a little more rigorously. Alright. So, dCn plus is the inverse of dCn minus. That means, what we now get to see is that this geometry is actually reflected in the algebra. It is just that you need to be able to read it. The geometrical changes are actually being reflected in the relationships between the transformation matrices, right. Okay. Now, I hope we have not forgotten this, that dCn plus is equal to dCn minus transpose, right. So, I can write, instead of dCn plus, I can write dCn minus transpose. dCn minus transpose equal to dCn minus inverse. So, as Rahul had said, you are Rahul, right. As Rahul had said correctly, these are orthogonal matrices. Okay. These transformation matrices, if they are real, then they are orthogonal. This is a demonstration of that. You can take some other basis, work out other matrices and check whether they are orthogonal or not. Okay. Hermitian is not a necessity, orthogonality will be there. Okay. And that is why we can invoke the great orthogonality theorem. If they are not orthogonal, how will orthogonality play a role? Okay. That is where we are getting very slowly. Fine. So, so much for your Cn plus and Cn minus. What was the basis here? Remember the coordinates, right? So, basically we are talking about transformation of a point, right. Now, let us do it in a little different way, but before that, if I write cos theta sin theta, there is a possibility that I myself will goof up. So, instead of cos theta sin theta, I like to work with some value.